Well, welcome everybody. It's glad to see everybody here today. My name is Monika Skonieczny, and I am the manager of the Trottier Institute for Sustainability Engineering and Design, also known as TISED. I would like to welcome all of you here in the room, as well as those joining us online, to today's seminar titled Light-Driven Environmental and Engineering Processes. This is the second talk of our TISEDTalks series, which was possible due to the generous donation from the Trottier Family Foundation. Before we begin, on behalf of TISED, I would like to acknowledge that McGill University is located on land which has long served as a site for meeting and exchange amongst Indigenous people. We acknowledge and thank these diverse Indigenous people whose presence marks the territory on which the peoples of the world gather today. A quick housekeeping note before we get started. After the presentation, we will have the standard Q&A period. If you are joining us online, feel free to enter your questions into the chat. We will give you an opportunity to, we will read out your question during the Q&A period, or we will give you an opportunity to unmute your mic and you can ask your question live to the audience. So we started this seminar series during the pandemic with really the intent to allow the members of our community to come together, present the great work that they're doing, and foster a collaborative environment that hopefully leads to further collaborations in research and really brings into the fold the entire McGill community and beyond. So we've done this over the last year virtually, and I am very happy to be able to be here in person to welcome today's speaker. So it gives me great pleasure to introduce Professor Stephanie Loeb, who's an assistant professor in the Department of Civil Engineering here at McGill. Professor Loeb's research interests encompass material science and environmental engineering, with particular expertise in the areas of nanotechnology, photonics, and environmental virology. The use of light, a ubiquitous source of energy, is a common theme among her research projects, which aim to understand how light from natural and artificial sources drive environmental processes, and to develop novel light harnessing material-based technologies for environmental remediation. Prior to joining McGill, she was a postdoctoral research fellow at Stanford, and she received her PhD in chemical engineering from Yale. She also holds a Master's of Applied Science in Civil Engineering from University of Toronto, and completed her bachelor's degree in physics and nanoscience jointly between U of T and the National University of Singapore. Please join me in welcoming Stephanie.
Thank you. All right, well, I am delighted to be here today to give this lecture and update on some of my recent research and what I've been working on since joining the faculty here at McGill. So I'm going to start off, even though we'll be talking about engineering and science today, but I'm going to start off with a small history lesson. So does anyone recognize this map? It's quite famous in environmental engineering, but we have a very diverse group here, so I'm not sure if anyone will know. So this is John Snow's map of London, England, from the mid-19th century. So he created this map in order to track a cholera outbreak that was sort of ravaging this area of the city at the time. So you can see there's many tiny black bars, but I'm going to highlight them here in red dots so you can see them easier. Each one of these represents a number of cholera cases. The size of the dot corresponds to the number of cases in that area. So at the time, there wasn't this understanding that water could be a vector for disease. So what Jon Snow noticed, and this is not Jon Snow of Game of Thrones fame, although maybe that's where the name came from, but he certainly predates that. So he noticed that at the center of where this outbreak was, there was a water pump. So this was the Broad Street water pump. And they identified that each of these houses collected their water from this pump. And aside from this, he did a series of interviews. He found 2 cases of cholera that were far outside the city, and he was able to track them to see that those houses had actually imported water directly from this pump. So it was very strong evidence, and this represents the first time that as a scientific field we were able to make this connection between infectious disease and water. So after this pump was shut down, the cholera outbreak subsided. So after we started to have this realization, it became quite common through the 1870s into the 1920s in Western Europe and in North America to begin using sterilization techniques that were already known in our drinking water, including most commonly filtration and chlorination. And this was done across Europe and North America. So after the institution of this, they found that cholera outbreaks, typhoid, other waterborne diseases dropped by almost 2/3 within 20 years, which is really a masterful result in public health. And today, centralized water treatment is considered to be one of the greatest achievements of the modern era in terms of protecting public health. So continuing a little bit about history, this is just moving a couple years forward from this innovation, this epidemiological study of cholera. This is what an old-timey chlorination system looked like. So this is one from 1918. So let's compare it to what a chlorination system looks like today. In reality, these systems work fairly similarly. The one in 1918 uses a solid form of chlorine to convert it into a liquid and pump it into the water treatment system. The one today uses a liquid directly. So let's think of the comparison to what we've seen in the water sector to a different type of technology. So this is what the phone looked like in 1918, and maybe you can guess where I'm going with this. But this is where a phone looks like today. These are almost unrecognizable, right? The amount of innovation that has occurred in the communication sector is massive compared to what we've done in the water sector, even though water is one of the most essential things in order to preserve life and promote health amongst our communities. So there's some reasons for this. I mean, maybe some people say chlorination works. If it's not broke, don't fix it. But there's actually a lot of issues with our current water treatment system that aren't being addressed. So one is infrastructure. Most of these, following the timeline that we've set aside here, most of our water treatment systems have been put in place in the early 1900s, and these systems are estimated to have about a 75 to 100-year lifespan in terms of the crumbling of the infrastructure. So you can see we're coming up on that deadline as we speak. There's also new contaminants that we weren't necessarily aware of in the 1920s. So at that time, we were focused on microbial diseases, which are still prevalent in our water treatment system, especially in places outside North America and Western Europe. But the EPA keeps track of contaminant candidates. So this is new chemicals that either we were there before, but we weren't able to detect them, or are newly emerging due to different industrial processes and different pollution mechanisms. But currently, there's 78 new contaminant candidates on the 2022 list, and the 2019 one had 90 plus contaminants. And those ones didn't remove from the list, they just went into actual regulation. So these are contaminants that are likely in the future to be regulated in our drinking water and wastewater systems. It's also very difficult to monitor. So if there's something wrong with our drinking water, it can be quite difficult to detect because of the vast amounts we have to produce every day. From the World Health Organization report, we also can see that still globally, there's 2.1 billion people that lack access to a clean water source, and still 1.8 billion of these people have no microbial treatment. So these diseases, these problems that were happening in 1920, this technology innovation has not been enough to fill the gap. So one of the big reasons that a lot of these issues persist is not because chlorination doesn't work. It's very effective for disinfection, but because there's a huge amount of energy that's needed in order to produce clean water and distribute it to everyone that needs it. So we call this the water energy nexus. And it's my feeling, and a lot of scientists in the field, that this is where we need our innovation to come from. How do we reduce the amount of energy that needs to go into our water treatment systems so we can more easily solve some of these problems of supply and quality, make sure that we're getting high quality water to enough people. So the opportunity really abounds at this intersection of water and energy to create innovation in a field that's really been falling behind compared to others. And this idea that there's a connection between water and energy isn't just intuitive, it can also be quantified. So if we look at two metrics, these are both from the World Health Organization as well. One is on the bottom here is access to electricity, and the other is access to basic drinking water services. We see that there is a correlation between lack of access to energy infrastructure and lack of access to a basic drinking water source. Now we can look at one other component. If I think of an area that's lacking access to energy infrastructure, I might think of off-grid technologies, something that doesn't require that you're hooked up to a main power grid. And the first thing that always comes to my mind is sunlight. So if we look at this from particularly how much sunlight isn't available in these areas that lack energy infrastructure, we can also see that there's a correlation, especially when you're looking at rural communities. So places that get more sunlight tend to also currently lack access to basic drinking water services. So this puts us at a nice confluence where we can look at how we can use sunlight in order to close this gap in terms of energy and water infrastructure. So normally I think when you think of solar energy, a lot of people think of solar cells. Solar cells are certainly great, and they can be a solution in a lot of situations, and they are ideal for a lot of applications. However, they're not essential to harnessing the energy that comes from light in order to drive these different processes, water treatment processes in particular. So you can imagine that the conversion of sunlight into electricity itself will probably result in a lot of loss of energy. So if we can take that light and use it more directly for our purposes, we might be able to develop more efficient technologies for targeting some of these problems. So today I'm going to talk about 3 different ways that I like to use sunlight to try and treat water. The first one is going to be looking at photolysis. So photolysis is basically using the sunlight directly. And what we're interested in studying in this case is understanding the viral photoinactivation mechanisms. And I'm focusing on viruses because they tend to be one of the primary etiologies of gastrointestinal illness, and also because they're relatively understudied. And as I show this work, this has been mostly done by 2 students in my lab. This is Yiding and Fernando that have been working on this project. And we'll get to the photocatalysis and plasmonics after. Okay, so starting to understand how do we know how this works already? So how can we use sunlight directly as a way to inactivate viruses? So this shows the solar spectrum here. These are the wavelengths that we're interested in looking at. We have the highest energy at the shortest wavelength in the UVB, and then down into the visible where we have lower energy wavelengths, at lower energy photons at longer wavelengths. So we know there's a few different processes that occur, a few different mechanisms that we can use to directly use these photons, which some of them, depending on the wavelength, can be biocidal in order to inactivate viruses. So if you imagine a virus, it's composed of 2 primary components. One is a capsid, which is made of proteins. You can think of it kind of like a sac that holds the genetic material, the nucleic acids on the inside. Some of these photons, high enough energy, the ones in the UVB regions, they can react directly with these components of the viruses to produce different kinds of deleterious photoproducts and prevent them from replicating, thereby preventing them from making you sick. We also know that in the natural environment, there's something called photosensitizers. So natural organic matter can be a photosensitizer, and the photons, instead of interacting directly with the virus, they can interact with this natural organic matter in the environment, produce reactive oxygen species. These reactive oxygen species can interact with the genetic components or the capsid components of the virus, thereby leading to various sites of damage that will also inactivate the virus. For some bacteria, it's also possible to have photosensitizers that are a natural part of the cell, but due to the simple structure of viral contaminants, this is very, very uncommon. So what we wanted to know is there's all these different types of viruses that have all these different types of morphologies. Can we better understand and predict how quickly and easily they will be inactivated by these natural processes based on the components, structural, and the natural morphology of the virus? So first, to do this, we wanted to find out, what does the field already know, right? This is a good way to get started when you're trying to understand and develop fundamental mechanisms. So we performed a meta-analysis, which extracts data from the known literature in order to quantify what's already out there. So we used 5 common enveloped and 5 common non-enveloped viruses, as well as several surrogates. And we started a review of the literature, and we were able to extract 16,000 unique publications that followed specific search terms that looked for the presence of the name of the virus, the use of inactivation, and the use of different solar wavelengths. From there, we were able to go through each of these different papers, which was a painstaking process that my students very diligently took care of. So you have 2 people review each of the papers to find out whether it meets specific inclusion criteria after the search. And from there, we were able to extract rate constants that tell us how quickly each of these different types of viruses is predicted to be inactivated using solar wavelengths. So these decay rates are given in terms of area over energy, right? So this is the amount of energy from the sun needed to achieve this inactivation. So here are the 10 different, 5 of each categories, viruses that we looked at, as well as the number of K values we were able to extract for each one. And you can kind of see it's not even. There's certainly things that certain people like to study more than others. So we broke this down also looking at the different types of wavelengths. So you can see by that process that I mentioned earlier that it's likely going to be wavelength dependent, these processes. So we wanted to understand, based on the type of light that's being studied and the type of virus that's being studied, what results are we expecting to see. So we found that non-envelope viruses are far more commonly studied than enveloped viruses. And in terms of the wavelengths that we're most interested in, it tends to be broad spectrum light sources that include both UVA and UVB. So comparing, this is for all different types of viruses grouped together. We can compare these 3 different wavelengths, and we see something that isn't particularly surprising, that when the wavelength is shorter, higher energy photons, we see that there's faster inactivation rate constants for all categories of viruses. We can also break this down to look at each of these wavelengths individually for our non-enveloped and enveloped viruses, and we found that the envelope viruses tended to have higher inactivation rates at all different wavelengths compared to the non-envelope viruses. So this is something we were relatively expecting to see based on the known mechanisms, but we also found a few very interesting threads that we want to dig deeper on while looking into this study. So the overall trends, as I mentioned, shorter wavelengths, higher inactivation, and we see that envelope viruses are more susceptible to photoinactivation than non-envelope viruses. But within this data, there's significant sources of variability and bias. And one of the reasons is that certain types of viruses are more commonly studied under certain conditions. So this might be what type of materials are in the matrix that's being studied, or what type of laboratory methods are used to study them. Some of this is based on just, practice in the field. They've always done it this way, so we continue to do it that way. And other of them relate to actual differences in the morphology of the virus that affect how we're able to manipulate it in the lab. So the 2 things that we were most interested in following up on, one is the presence of photosensitizers. So this curve is showing, this is a contour plot where we're showing the experimental matrix on the bottom here and the wavelength here. So we see some trends that we were expecting to see. As I mentioned, as the wavelength gets shorter, we see higher inactivation rates. We also see that as we move to media that we know contains different amounts of photosensitizers, more photosensitizers tend to lead to higher inactivation rates. And this is more important for longer wavelengths as opposed to shorter ones. It could mean that these photosensitizers also are able to block the light or affect the absorption of the virus in some of these cases. But especially at these longer wavelengths, we see almost like a moderating effect. And this is important because envelope viruses are far more likely to be studied in culture media compared to in air, water, surfaces, more clean environments. Another one that we found was very interesting is comparing the enumeration method. So by this, mostly I mean the difference between doing a culture-based system or a molecular-based system. Molecular-based system typically meaning a PCR. So if we look at the different viruses and the different ways they've been studied, we can compare the results we get from if it's studied using a plaque assay or if it's studied using qPCR. And we have understanding, which I'll talk about on the next slide, that qPCR tends to underestimate the infectivity of the virus. So if we have a virus where it's very unlikely that culture-based methods are being used in the lab, potentially because they don't exist or they're very impractical to work with, then all these K values that we're getting are biased towards representing a lower value than maybe necessarily they would get using a plaque assay because they're studied using qPCR. And there's a few viruses in particular that we see this with. Calicivirus is almost always studied using a plaque assay, same with rotavirus. And you see that the plaque assay is reporting significantly higher inactivation rates than the qPCR. So this idea that qPCR isn't the same as infectivity, we wanted to dig into this a little bit deeper. It can be quite a problem in trying to understand inactivation kinetics. And the reason that this differentiation exists is 2 reasons. So typically, qPCR looks at just a small fraction of the genome. So here, imagine you have 1,000 base pairs, but you might be assaying only 50 to 100, even 150 would be fairly long. If the damage site from whatever inactivation method we're using, here we're focused on sunlight, so if the sunlight damage occurs outside that region being tested by the qPCR, you won't see it. You'll get a false positive. So you'll end up not being able to find as much damage as is actually occurring. It could also be that the damage occurs in different parts, different components of the virus. So if the damage is to the capsid and it releases the genetic material into the matrix, you can still detect that intact genetic material even though the virus has actually been inactivated. And this can be very important for a number of different important viruses. And one of the main ones is human norovirus. So human norovirus is likely, by most estimates, it's a difficult thing to estimate, if you get sick from drinking water or from swimming in water, it's probably norovirus. It's the most likely one in each of these cases, especially for recreational waterborne illnesses. So it has a genome length around almost 8,000 bases. And currently, we don't have any good culture-based methods for working with this virus. It's very difficult to work with in the lab. So almost all the studies on its persistence in the environment have been done using qPCR. And this means that they probably are vastly underestimating the actual persistence of the virus in the environment. Now, an underestimation is probably better than an overestimation, but it still makes it very difficult for planning things like, where do we put our beach, where do we put our wastewater outfall, because those are still things that are needed, and we want to understand how long it takes for this virus to be inactivated by natural processes. So there has been a way that we've developed to kind of get around this, and it has this assumption baked into it, and we call this assumption the single-hit inactivation model. So we are assuming that in order for norovirus, or whatever virus we're working with, to be inactivated, that it only needs to have a damage site in one location in its genome. Example would be here. So let's say a photon has struck this area of the genome. It causes a photoproduct. When we're going for replication, whenever the enzyme comes across this, it doesn't like it, stops replicating, our virus is inactivated. So we assume that it only takes one of these photoproducts in order for this to occur. So if we're doing an assay, a qPCR assay, if the assay happens to fall within this region of the damage, then that's great. We'll detect that it's damaged and our virus is dead. But as I mentioned earlier, usually 500 would be very long. That's about as long as you could get for these types of assays. If it happened in a different region, we wouldn't detect this, and then we would get a false positive. There's a method that we can use to try and compensate for this, which is assaying several regions, several different relatively long regions of the virus, and then combining the results that we get from each of them using a Poisson distribution to back calculate the likelihood that that virus contains no damage sites. So we call this the single-hit Poisson extrapolation, and it's a method that's been used to try and correct qPCR data to get it closer to a plaque assay. However, in order for this to be accurate, the single-hit model has to be valid. We know the single-hit model is valid for UV254, which is UVC light, which is even higher energy than what's available in sunlight. But we don't know whether this is going to work for sunlight or not. The current paradigm is understood that the damage mechanisms are very similar, but maybe we'll find out in the next couple slides that that's not exactly the case. So the reason that we wouldn't necessarily get exactly the same results, even though both of them are photoinactivation mechanisms, is how different the spectrum is. So here I'm showing the spectrum of a mercury lamp, and here is the spectrum of a solar simulator roughly matching sunlight. The rainbow one here is actually directly is an actual sunlight measurement. So we can see that we're looking at really, really different types of wavelengths, different photons that are present in the system. So for this study, we looked at doing this Poisson extrapolation at a few different wavelengths to test the wavelength dependency of this inactivation model. So we used sequential long-pass filters to modulate the amount mostly of UVB light that we had present in the system to see the effect of UVA and UVB wavelengths on norovirus using this model to compare it back to see whether this single hit is valid. So in order to do this, we took two viruses. We were using human norovirus as well as a surrogate MS2. And we have to use a surrogate because we need to have culture data to compare it to. And norovirus, only very specific places are able to culture this. It's a very difficult process. So we were able to get information both on the culture-based study for MS2, as well as the qPCR for MS2 and for human norovirus. So what I'm showing in each case, each of these colors represents a different type of wavelength. So the light this is the cutoff filter here. So only wavelengths longer than that in each of these cases. So you can see as we're cutting off more and more wavelengths, we're decreasing our inactivation. And in the dark, we see basically nothing because this is a sunlight-driven process. So this is the results that you get culture-wise for MS2. This is what you get from qPCR. just taking an average of the results from those 4 amplicons, not using the Poisson distribution process to account for damage in different locations. You can see, of course, it's vastly underestimating what we expect to see. But the interesting thing is when we do this extrapolation, we actually see that it greatly overestimates the amount of inactivation. So we perform the same thing for human norovirus, but without a culture to compare it to, it's hard to know exactly how those results compare. But this is not what's expected if the damage follows the same model that we have for UVC. So the single-hit Poisson extrapolation greatly overestimates the infectivity from the plaque assay. So we know that the sunlight damage does not follow this rule. It's very likely that this single-hit model that works for UVC inactivation does not work for sunlight. So there's more complicated mechanisms going on there that we're not quite capturing. So what could this difference be? So one thing we thought about was just looking at the genome. What differences could the damage in the genome have to mean that we see this model matches for UVC, but it doesn't match for sunlight? So what we did is we took the different qPCR assays that we use, the different amplicons, and we looked at what type of base pairs were present in those sequences. So we know that certain configurations of certain base pairs are more likely to produce certain photoproducts. The primary one that we see as being damaged in UVC systems is the formation of pyrimidine dimers. So if you have 2 U's next to each other, 2 C's next to each other, or even a UC next to each other, it's possible that when they're hit by a high-energy photon, they form a dimer, and that dimer is a type of photoproduct damage that prevents the virus from replicating. However, at longer wavelengths, maybe around 280, maybe getting down to 290, it's known but has not been well quantified in the literature that you can also form hydrates, primarily uridine hydrates. And in this case, you only need 1 U base pair. And these hydrates are considered to be important damage, but not necessarily as deleterious as these pyrimidine dimers. So although they form, they may not be as long-lived, and they're very difficult to quantify. So one of our hypotheses is that for sunlight, because we're looking at lower wavelengths, the formation of these dimers might be less common, but the formation of these hydrates might be very common. And if the formation of these hydrates are common, it might mean that we need more than 1 damage site, if they're able to repair, for the virus to actually be inactivated, which could mean that this form of genomic damage isn't properly corrected for in the single-hit model. So to see whether we could look at the results that we got from this study to get any inference on this, we tracked the rate of degradation of each of our amplicons based on the differences in their structure. So here we're tracking the percentage or the number of locations that each of these amplicons have of each of these different configurations. So you can see how it changes depending on which type we see. So we found that there really wasn't any connection in this case between the number of pyrimidine dimers, or the number of U's next to each other, the number of these paired pyrimidines next to each other. We found that there wasn't any link between that and the likelihood that the amplicon saw greater inactivation. So there's no evidence that these dimers are the primary mechanism that's driving photoinactivation. In terms of determining whether it's the uracil hydrates on their own, we weren't able to have enough statistical significance in this case because you're only talking about 4 base pairs, the presence of one of them, it was about 1/4 for each of them. There wasn't enough difference in the amplicons to determine that. So it's something we're interested in looking at in the future. Another way of understanding the damage that might be occurring or why it doesn't fit this model is if the single-hit model doesn't work, it could be because the damage is not occurring on the genome. It could be occurring different locations on the virus. So another thing we looked at is assaying the structural change to the capsid. So in this case, you have your capsid, your structure here, that releases this free DNA. And if we don't do anything, when we do our qPCR, we detect this free DNA. But what we can do is do a pretreatment where we use an RNase enzyme in order to degrade any free viral RNA or any RNA that might be inside a damaged capsid. So you're basically neutralizing this RNA that the qPCR should detect but shouldn't really count in the system. And what we found in this case was that this capsid damage seemed to be very important for norovirus, but not so important for MS2. So in the end, there's a lot of questions left about the different virus morphologies and different ways that these inactivation mechanisms are interacting. And in terms of damage to the capsid, as well as the differentiation in the damage to the genome, is something that we're interested in looking forward in future studies. Okay, so now that we talked about photolysis, so this is just using the sunlight directly, we're going to get to some ways that we can take the light and sort of augment this process, make it more efficient using different types of advanced materials. So 2 materials that I'm interested in looking at are photocatalysis and plasmonic materials. And I want to highlight that work in this area in my lab is being done by Sadia and Grayson. So first we'll talk about plasmonics, and then we'll come back to photocatalysis. So what are plasmonics? These are typically small metallic nanoparticles that have free electrons oscillating on the surface. So because they're confined into these small particles, these electrons have a characteristic oscillation frequency. When this frequency interacts with sunlight or different wavelengths of light that are resonant with that frequency, it can produce an amplification that creates an electric field around the particles. This electric field interacts with these wavelengths of light in a very interesting way that we can manipulate in a number of different ways in order to drive environmental processes. So let's break down how this works into different sections. So first you have your plasmonic nanoparticle. It has this oscillation, this electric field around the surface. This helps draw resonant light towards the particle. So it actually redirects the flow of light towards a particle, able to capture more light. They're actually able to capture more light than their geometric cross-section because of the electric field enhancement around it. After it absorbs light in these wavelengths, you'll have a photoexcitation of hot electrons from the particle. We can take these hot electrons or hot holes, hot carriers, and use them to drive chemical reactions. Or if they aren't used to drive any chemical reactions, this energy will relax back into the lattice and eventually into the environment, and it creates intense heating around the particle. So we can use this property of these metallic nanoparticles to both drive chemical reactions or to generate heat. So we use these, in our first study we thought, well, heat is a very effective way to inactivate microorganisms, so we'll look at the photothermal component of these materials. So we synthesized 2 different types of materials known to exhibit these properties. One is a gold nanorod, and the other is a broadband absorbing carbon black material. So the gold nanorods can be synthesized using gold chloride salt. Then you add a strong reducing agent, sodium borohydride, and a capping agent here, CTAB, to control the growth. You combine these together, it makes small gold seeds. From there, we add a slower reducing agent, ascorbic acid, to make cubes, and then we can add silver nitrate, which acts as a directional agent to control their growth to generate these rods. The rod shape is actually very important in this case. If you imagine you have the oscillation of your electrons around your particle, if you have a unsymmetrical and isotropic particle, you can end up with 2 different plasmon modes. One relates to the oscillation on the longitudinal axis and the other on the radial. So that's what we see here for the nanorod. You see a big peak on the longitudinal axis, and then you see this smaller peak on the radial. So it allows you to absorb light in 2 different locations. From here, we wanted to take these materials and put them into a mechanism that we could use for water treatment, for disinfection. So what we did is we combined them into highly dense films and then measured the temperature that we could achieve on the surface. So to get high concentrations of these particles into films, we further stabilized them using a polyelectrolyte. So this polyelectrolyte is negatively charged, so it has opposite charge of the CTAP that's on the surface of the gold. It compresses this capping layer and makes it very, very stable. This allows us to disperse very, very high concentrations of the gold nanorod into several different solutions. We started with acetone. The acetone we then dispersed into a highly transparent polymer, transparent to both UV and visible wavelengths, that allows these nanomaterials to still absorb light. So here's what each of these films look like. So we did this using both the carbon black and the gold nanorods and a combination of the 2. This is reflectance data, so we actually want it to be as low as possible. So if it's not having any reflectance, this means that all the light that's striking these films is being absorbed, and we hope being transferred to localized heating. So in order to measure the heating that's occurring at this surface, it's very localized around the nanomaterial, so you can't just stick a thermometer on it. So a different mechanism that we use to do this is using quantum dot nanothermometers. So these quantum dots have this very interesting property that when they heat up, the lattice expands. And because the type of fluorescence that comes from these quantum dots relates to quantum confinement, as the lattice expands, it actually shifts the wavelength of light that you see from that fluorescence. So we can see, here's an example of cadmium selenide quantum dots that have been excited with a 447 nanometer laser at different wavelengths. And you can see that the intensity of the light drops off with temperature, but then we also have a red shift. And this is much more useful to measure because there's a lot of different things that can affect this, scattering, absorption. It's very difficult to use this as calibration, but we can use this red shift that we see in the peaks in order to measure temperature. So we took our quantum dots and we applied them onto the surface of our photothermal materials. We let this dry overnight, and then we used a laser fluorescence system in order to measure the wavelength shift in the quantum dots. So we have our solar simulator that we use for the heating, and then the laser, which is just briefly flashed in order to get the excitation, which is collected from a monochromator, and can give us very accurate measurements of the wavelength. So in order to do this process, the method that we found was best is it's difficult to do this with the solar simulator on because it creates a lot of background. So we would heat the films and then take a quick flash with the laser in order to produce the right fluorescence, and then we would measure the rate of cooling of the film. And from there, we can put this back into a 1D heat transfer model to predict what the maximum temperature of the film was right when we turned off the solar simulator. So we got some pretty interesting results for this. For the transparent film, this is what we expected. It heats up a little bit. You're still shining, you're still putting energy into it, but it doesn't get very hot and it cools off relatively rapidly. And we see for the carbon black and the carbon black nanorod containing films, they achieve temperatures over 100 degrees within this is 3 minutes here, this is 1 minute, so it's almost 100 degrees after 1 minute. And then it cools off back to room temperature. We also see that the carbon black film takes longer to heat up, although it eventually achieves overall higher temperatures compared to the gold nanorod film. The composite is the one that we thought was performing best in this situation. So in order to test these for a water treatment scenario, we printed these small-scale 3D printed reactors, which have a tortuous flow path. We then put the nanomaterial film into the surface of this reactor. We run water through it, containing, in this case, we use MS2 bacteriophage as a surrogate for the inactivation. We run the water through it, and we measure how many pathogens are left at the end. So you do see some reduction in the dark control. This is because there's some absorption to the surface of the film itself. The transparent film, you see a little bit more, right? This is our photolysis that's still happening. But we see a much greater reduction when we're looking at our film containing either our plasmonic material or our carbon black. So we did this to kind of prove that this was the heating. We also did this starting at 4 degrees, and you can see starting at cooler temperatures has a huge moderating effect in the amount of reduction that we see. And then first we tried this just with the nanorod, and then looking at our other films, we see much greater inactivation using the carbon black or the composite material. So we wanted to model what was going on in the system in order to see whether we could predict the likelihood of scale up. So we used a COMSOL model and particle dynamics, which we had developed earlier using tracer tests, using fluorescent microcapsules that I'm not showing the data here for. But we used those predictions in order to put this into a COMSOL model and predict what the temperature is throughout this system, right? So I'm just taking this multi-flow channel and putting it into one long line. So we can see that the temperature in this system is reaching up to about 80 degrees in the bulk, and that's significant and effective for inactivation. For MS2, we predict that it only needs to be treated at 75 degrees Celsius for around 1 minute in order to achieve significant inactivation. So using this model that we had validated on the small scale, on the bench scale, we scaled this up, increasing the flow rate to achieve the amount of water you would need practically, which is about 8 liters of water per day, in order to have enough for a family of 2. And we found that in order to do this process, you would need 60 by 60 centimeter kind of platform film in order to achieve enough water for a household of 2. So that's not a huge area, it could be feasible. So there would be some way to improve this. Improving flow dynamics, increase contact time. It's possible to increase this footprint. We also looked at, this is just from modeling, not from experimental results. We also looked at putting thermal insulation so that you're not losing heat through the surface. And we predicted you could decrease the footprint by 4% if you had close to perfect thermal insulation, which would obviously be challenging. to achieve. So the last material I want to talk about briefly is photocatalysis. And this might be one that, from an engineering standpoint, that people are a little bit more familiar with from water treatment. It's one that's known and used in the water treatment field relatively regularly. So the primary material that we're used to seeing for this is titanium dioxide. So how this works is you have energy of a certain wavelength higher than the band gap of your material. Strikes your material, and you'll have a promotion of an electron from the valence band into the conduction band. From there, you take this charge carrier separation. If the carriers can migrate to the surface of your nanomaterial, which is why having them nano-sized is very beneficial, it can interact with oxygen or water in order to produce reactive oxygen species, which can then degrade a number of different pollutants and work effectively as a disinfectant as well. However, there's a lot of negatives currently to the industrial standard material for this. One is that TiO2 has a relatively large band gap, a wide band gap, and it only is capable of using the highest energy photons available in sunlight to do this process. Only about 5% of the photons that are available. Also, our candidate benchmark material, TiO2, has a relatively high rate of recombination. So although we produce these charge carriers, they have to migrate to the surface in order for this process to occur. If instead they relax and recombine, then you close your loop and you don't end up with any treatment process. We also find that once you get into the bulk of the water, hydroxyl radicals, which are the different reactive oxygen species that might be produced, they can be scavenged by all kinds of different things, even just alkalinity, some things that we don't necessarily need to break down, so we end up wasting a lot of the chemical species that we produce. So this material has been around maybe 20, 25 years, but it's never really been uptaken by industry. And these are some of the reasons for that. So recently, we held a debate in the field, and this debate became a feature article in ES&T. So if you're interested in reading a little bit more about the history of photocatalysis, I recommend this. And it identified some of the primary research barriers that we have to this technology working at full scale. And one is certainly higher efficiency for these materials, reactive design, and understanding what applications it's going to work for specifically. So in terms of just broad water treatment process as disinfection at full-scale municipal plants, maybe this isn't the best technology, but there could be some niche applications where this might work really well. So one thing that we're very interested in doing in my lab is enhancing this process and designing it to work with specific types of chemical reactions that can't be driven by current technologies. So there's a lot of components of this that we can control by engineering the material in different ways. So we know that we have this initial process. Let's say we have some very difficult recalcitrant contaminants in water. Some of these can be broken down by hydroxyl radicals. Some of them might need more higher energy species in order to do this. But the goal is to take a contaminant and turn it into just benign products and CO2 and H2O. We call this complete mineralization, which in practice is quite difficult to achieve. So we can do this using the reactive oxygen species, but it can also be done using direct reactions with the electron and hole. So you don't necessarily need to go through this process. You could have the electron or hole interact directly with these contaminants. And we can control the energy, the separation energy between these two species based on the band edges that we have for our semiconductor material. So synthesizing different semiconductor materials can change what the energy of both this electron and hole are. For our plasmonic materials, incorporating them into this, they have a number of different benefits. So the plasmonic material has a specific resonance, and it will attract light within that resonance, in the area of its resonance. So we can synthesize different plasmonic materials with different peak resonance in order to focus the absorption of the light into the light that might match best with this band gap. Or we could look at using lower wavelengths of light in order to get electron promotion from the surface plasma resonance material into the photocatalyst. There might be a few other methods that also help, that these plasmonic materials can help achieve better results from overall photocatalysis. There's also this idea that it might decrease the depth of absorption of the photon. So if the photon is absorbed closer to the surface, the carriers are produced closer to the surface, they don't have to migrate as far, reduce the amount of recombination. So there's a lot of benefits to this system. So currently in our lab, we're working on two different mechanisms of developing plasmonic enhanced photocatalysis. One is using a bimetallic silver-gold alloy. These are quite fun to synthesize because they come in different rainbow colors as you move forward. So this is pure gold, this is mostly silver, and as you change the ratio of the two of them, you can very easily, I say relatively easily, I don't do this synthesis, the student does it, so I'll tell you how easy it is. You can change specifically the wavelength you're looking at by changing the ratio of gold to silver. So we can very finely control the plasmon peak of our materials. So we've been able to combine these with TiO2. You can see here the bulk TiO2 material. These small dots on top of it are the plasmonic materials, which are relatively well dispersed throughout the particle. Another type of material we're looking at is using broadband aluminum. So aluminum is a plasmonic material that tends to absorb in the UV range. This can be very beneficial for a number of reasons, but mainly it's if you're thinking from a cost perspective, it's much more advantage to use aluminum compared to silver and gold. We've been able to synthesize materials also containing a combination of titanium and aluminum. So moving forward, we're looking to testing some of these materials with a few different chemical contaminants. Okay, so I want to thank everybody for listening. I had a great time talking to you guys about my research today. I'm happy to take any questions. I want to acknowledge some of the collaborators and, of course, my fantastic research group that makes all this possible. Thank you.
Maybe I can ask a question. Thank you very much for a very fascinating overview and introduction of new concepts like the plasmonics that we talked there. So I was, so you say of the three options, the photocatalysis is the less, it's the most developed and applied, but you were more critical of that than the other two. I guess the other two have not grown up to be adults and be criticized with their limitations, but with TiO2 photocatalysis we have seen the limitations over the years. So let me ask you, what about extending to visible light the activity of TiO2 by doping or other type of modifications? What is there? What do we see happening? Is it really a practical option? What's your opinion?
I think, so one of the difficulties with extending to visible light is you're reducing the band gap of the material. So a lot of the methods that have been developed so far, they add, as you're saying, these doping sites. So you reduce the overall band gap, which allows it to work with these visible wavelengths, but it also tends to result in a lot of recombination. So currently, the technologies that have been developed, although they're able to widen the spectrum, it often comes with a reduction in the quantum efficiency, and the material itself is not out-competing the TiO2 that has the wider band gap. So that's been one of the major drawbacks. So if someone can solve that problem, I think that's still huge, like in terms of material development. For us, we've kind of taken this alternative approach is maybe we can improve the light absorption without decreasing the band gap. And that has the added benefit that we can maintain these higher separation between the charge carriers. Hopefully we don't get as much recombination, and also potentially drive chemical reactions that have a higher redox barrier in order to do that. But yeah, I still think there's a lot of changing to visible light can be beneficial in quite a few different categories, but I haven't seen a material recently that I've been very impressed with. Yeah.
Any other questions from the room?
If not, I can continue.
Go ahead.
So talking about TiO2, you show plasmonic approaches. You add your gold, silver, the biometallic or the aluminum. So how that works to improve the efficiency? Yeah, there's a light antenna effect from the plasmonic. So do you down convert to UV, or I should say, there must be a change in wavelength of the light due to the plasmonic component. Can you elaborate on that, please?
Yeah, so for the aluminum, the goal is to synthesize them so it matches the wavelength of the band. So in that case, you're aiming to increase the absorption of just the highest energy. So let's say, the band gap is around 300, right? So we aim to achieve a plasmonic material that has that same resonance frequency. So that is focused on using the light antenna effect and potentially some of these other, charge carrier withdrawing effects in order to reduce the recombination. For the gold silver, that's definitely looking at widening the type of photons that you can use. And in that case, it's probably, the mechanisms for this are still relatively debated. And we have an interest in doing some wavelength-dependent studies to kind of tease them out. But for the gold and silver, we're looking at using more visible light around 500 nanometers, where it's probably an electron injection process in order to achieve that. So that one, the gold and silver, we'll look at using visible, where the aluminum focuses on UV, probably to drive different chemical reactions. So the aluminum, we might focus on maybe fluorinated compounds or something where you need very high energy species in order to break those bonds. Or for the aluminum and the silver, we probably look at pharmaceuticals and other things that can be broken down using hydroxyl radicals.
Okay, thank you.
Yeah. Question?
Okay. Well, thanks for the nice presentation. A couple of questions actually. One is, so in terms of mechanisms of inactivation or degradation of chemicals and so on and so forth, what is the role of like the water composition in terms of the ROS being used up by, let's say, nitrates? I mean, there are things that are going to be in natural water that relatively, sort of processed water that you can't get rid of. So how would that affect efficiency?
Yeah, I mean, it will a lot. Yeah, I think there's different things that we worry about depending on different processes, and a lot of times, especially when we're looking at disinfection, there's been quite a bit of study looking at using TiO2 for disinfection. It also doesn't really go anywhere because of a lot of these problems. It's just using the ROS that's developed from a wide bandgap semiconductor, it gets eaten up by all these other things, and it's not very effective as a disinfection technique in water that hasn't been highly processed already, right? And if you're talking about a disaster relief situation, you're not going to have water that's missing organic matter and missing all these things. That's why in terms of like disinfection and disaster relief kind of situations, there's a bit of an edge to the thermal process since it's not impacted by that in the same way. But if we're looking at targeting specific kind of contaminants, then I think for photocatalysis, it's really got to design the material specific to the application. So if you're looking at like a potable reuse scenario, you might have only those few things left you need to get rid of, right? It might be the final step, or really like more of a polishing step than something that's done. But certainly where it's placed, if it's placed in a water treatment train, where it's placed is very important to whether the processes can be conducted effectively or not. But typically scavenging is hugely detrimental to anything that makes hydroxyl radicals, yeah.
But in polished water, I mean, except where you need to get rid of a few molecules or a few viruses, it's practical in your opinion?
At full scale, I mean, it's never been done yet. So maybe if we can, I think it can be practical if we can improve the efficiency of the materials, not with the materials that we have now, I think.
Are there any questions in the chat?
No.
No questions. Yes, maybe one last question. If there's anyone else who would like to pose one from the room?
I have, if I don't mind, can you explain for someone who knows nothing about viruses and etc., what is the difference between enveloped and not enveloped?
Oh, sure. Yeah.
Viruses that you're saying, oh, the envelope. I know the envelope, but
Yeah,
nothing else.
yeah, that is a good question. Yeah, I think so. This one, some of these terms, I think after COVID, people became almost like too familiar with some of them. But yeah, that one is. Two major differences in there's many different differences in morphology for different viruses, can be different genomic structures, but an envelope is a big one that affects its persistence in the environment. So I described these two components, the genetic material and then the capsid. So ones that are enveloped, they have an additional structure on the outside, so it's a lipid bilayer, an envelope that comes with the surface. You would think having this additional structure would give it more environmental protection, but it tends to be not, the envelope itself is essential. So if the envelope is broken, then you can assume that the virus is relatively ineffective. So damage to the envelope tends to be faster, happens quicker than damage to just the capsid and genetic material on its own. So they tend to be less persistent in the environment. So coronavirus is envelope, so less persistence in the environment.
Coronavirus is envelope.
Yes.
Okay. So with that, thank you again, Mr. Loeb, for your presentation.